So we have Isaac Kim from very far away, UC Davis. Tell us about more about maybe computing Hamiltonian or more. Please.
Okay. Hi, my name is Isaac Kim, and I'm going to tell you about this joint work with Daniel Ranard. We're hoping to put it out on archive in a few months. We'll see how it happens. Anyway, this is about the classification of 2D ground states with the strict area law. So area law is an observation that in many physical states of interest, the entanglement entropy of a subsystem is bounded by roughly its area. And this is somewhat surprising because if we consider a generic quantum many-body state, according to the Haar measure, typical states obey the volume law of entanglement entropy. So this suggests that many physical states of interest, such as the ground state or Lorentz excite states, have some special properties. And our goal is to understand to which states this happens and how to exploit that structure to our advantage. A very well-known fact is that the area law has played a very important role in our understanding of one-dimensional quantum many-body systems, especially systems which are gapped. These are many-body systems in one dimension, such that the lowest energy, the difference between the lowest energy and the first excited energy is bounded from below by a constant. And it's known that for such systems, it was proven by Hastings that if you cut your system into half, let's say left half and right half, no matter where you place the cut, the entanglement entropy is bounded from above by a constant. And this has led to very important consequences. For example, it implies that the underlying ground state can be well approximated by a matrix product state of a moderate bond dimension. And this subsequently implies many of the central results that we know and love about one-dimensional quantum many-body systems. For example, there's an efficient classical algorithm for estimating the ground state energy. There's a heuristic but nevertheless very effective method developed by Stephen White, known as the DMRG method. And there's this very nice rigorous algorithm that works provably well for one-dimensional gap systems. And at this point, we also have a full classification of 1D gap systems. What this means is that we are interested in classifying a set of quantum states that can appear as a ground state of a one-dimensional quantum many-body system. And we want to classify them according to some equivalence relation. And basically the rule is that if you have two ground states which are adiabatically connected to each other by some path, then they are deemed to be in the same class. And we know, we essentially know the answer to this problem, which is very nice. So ideally, we like to replicate the success in higher dimensions, let's say in 2 dimensions, in 3 dimensions. But many things are very, very murky. Many things are unknown. So there has been some nice progress in trying to prove some form of area law. But unfortunately, in all the results that we have, we need some kind of additional assumption or at least alternative assumptions. So there are ways to prove that, but this is still a work in progress. Like proving the area law from the gap assumption alone is an outstanding challenge. And moreover, even if somebody proves the area law in the future, as of now, it's not totally clear what that would entail. In 1D, this already told us that the underlying state can be well approximated by a matrix product state. So you would hope that area law in higher dimensions also imply that the underlying state can be well described by some tensor network, let's say PEPS, for example. However, unfortunately, this cannot be true exactly. So it was shown by Gay and Isert that the class of states that satisfy area law is too large, so that you cannot hope this set to be well approximated by the polysize tensor network. Of course, I should emphasize that this doesn't mean that we should stop trying to prove area law. The techniques that going into proving area law may actually help us in arriving at these desirable conclusions. I'm just saying that area law in itself is not going to allow us to conclude this. To be clear, our work does not make progress on this important problem. That's for the future work. And we want to consider a different problem. This is a problem in which we assume some version of area law, a stronger version than merely assuming this like upper bound on the entanglement entropy, and trying to arrive at the consequences that we can hope that we maybe hope to achieve in the future with its full generality. So we're going to propose a slightly stronger, a much stronger actually, but hopefully still reasonable condition under which some surprising consequences can be derived. And the assumption that we make is what people call as exact area law or strict area law. So usually when we say area law in the most rigorous sense, what we mean by that is that there's an upper bound on the entanglement entropy, which scales linearly with the size of the area. However, in many physical systems of interest that people have studied, you often find that you not only have this upper bound, but you also have some exact form of the entanglement entropy. And that form includes a term that is proportional to the area, which is the leading term. And there's a sub-leading term, which is a constant, which is independent of the microscopic details. Of course, proving such things is like extremely difficult. And as a matter of fact, I should note that this is not even correct in general. So nevertheless, let me just first point out what our result does, and then tell you what I think about these caveats. So here's the result. So suppose you have some two-dimensional quantum many-body systems on like a disk. Let's say it consists of qubits or qubits. Okay? And you assume that this exact strict area law condition is satisfied everywhere. Then our claim is that there is some constant depth circuit, such that after you apply that circuit, this state can be converted into a state that is already well studied in the literature. It is a ground state of a model called as the generalized stringnet model. I will tell you more about this model if you've never heard about this. But let me just tell you about the brief history behind this model. This was the model first proposed by, good. So everything that I say in this talk will be like a 2D local.
Does this constrain the possible gammas one can have?
They do, yes. Yeah.
So there's gammas for which there's no state.
Gamma is like 0.2 or something. There is no such state. Right. So there is a model called the stringnet model that was originally proposed by Levin and Wen in 2005. And back then, they formulated some class of models. And when you look at the formulation, there are some assumptions that they make. However, later it was realized that there are some topological order systems which lie outside of this original formulation of Levin and Wen. It turned out that there are some assumptions which are actually unnecessary. So these details were flushed out around 4 years ago by these people. And now we have a more general version of the stringnet model. And this is what people call as the generalized stringnet model. Okay. So of course, the big disclaimer is that the strict area assumption is very strong. And it cannot be true in general, even for commuting local Hamiltonians. And this fact was first pointed out by Sergei Bravy, although he never wrote a paper about that. In the literature, this is known as the spurious topological entanglement entropy. So the way I think about our result is that obviously in the long run, we would like to prove area law and then arrive at a result like this. This is like a simplified but still general enough toy model to solve this challenging problem. So it's a little bit of partial progress.
The generalized stringnet model commuting Hamiltonian?
Good. So yes, but yes. That's it. Yeah, let me talk about that. Good time. So as a high level, this generalized stringnet model is a local commuting projector Hamiltonian. So on that ground, it's a nice model to deal with. And once you write down the Hamiltonian, say on a disk, it is easy to verify that the kernel of this Hamiltonian is non-empty. So this is not always easy, but for this particular family of Hamiltonians, there's just a well-known argument for that. And you might be familiar with the toric code. That's just a very special case of this generalized string net model. And here's a more detailed description of this model. It turns out that, as I said before, this is not just a single model, but for a class of models. And there's a data that defines, there's an input data that defines this model. And this is a unitary fusion category. If you don't know what that is, don't worry about it. It's just some abstract data. And the most pedestrian way to think about this is that it is some finite dimensional tensor. And it obeys some algebraic equations, like two algebraic equations. One is basically saying that some matrix is unitary. Other is some consistency equation that we do. So it is some fixed finite dimensional tensor, and that defines your model. For the case of the toric code, it would be the representation of Z2. More importantly, there's in the physics, like a topological phase community, there's a pretty plausible conjecture that we can make. And it is that any gapped Hamiltonian on a 2D disk is likely adiabatically connected to this model for some choice of unitary fusion category. Obviously, proving these things is like ridiculously hard. So we cannot like just assume that this is true and prove things. But we can at least make some partial progress in this simplified setting. Okay, so let me tell you about some motivations. So one motivation is about the complexity of commuting local Hamiltonian, which Jing very nicely introduced. So Jing told us that she thinks that this is probably in QCMA. Personally, I think at least for 2D, this is in NP. Of course, this makes life more interesting, obviously. But the reason is that it is believed that every 2D commuting local Hamiltonian on a disk is likely connected to this generalized string net model by a constant depth circuit. Obviously, we don't know if that's true, but the point is that if this is true, then there's a very simple NP witness that shows that proves that let's say the ground state energy is below some quantity. And the idea is the following. There are very general properties of the string net that once you write down to Hamiltonian, its kernel is non-empty. So you know that there is some ground state. There is a state with zero energy for this Hamiltonian. And it turns out that this model satisfies a condition called as a local topological quantum order condition, which basically guarantees the consistency of the density matrix for local ground states and global ground states. And this is just proven. In order to compute the reduced density matrices on constant size region, it suffices to just compute the ground state of some local region using some Hamiltonian and some local patch. And then you evaluate the density matrix in the interior. This obviously takes only a constant amount of time. So as an NP prover, you can simply give the description of this the string net, generalized string net Hamiltonian, and this like a constant depth circuit. And from this, you can just evaluate any local term, expectation values of any local terms in your Hamiltonian.
Yeah. So could it be a P prover? I mean,
good.
What's the question?
Could it be a P prover? Yeah, I'm not sure. That seems rather strong, but I don't know. Yeah.
So this O1 size ball depend on the gap?
The gap is 1 in this model because it's commuting projector.
But it should be inversely proportional to the gap if you were.
Oh, sure. But this model has a 0 correlation length. So it's yeah. I mean, well, actually, like any O1 size region which is small compared to the system size, this can be computed. Well, actually, yeah, I'm not sure, but my comment only pertains to this constant size region.
and these models satisfy exact area law.
That's right. These models satisfy exact area.
So, do you know that this problem is in QCMA? Like, if you don't have if you have polydepth circuit, do you know?
Oh, these models. I would strongly believe that there is a log depth circuit.
Log.
Yes, yeah. Although the original StringNet model, there people have like Koenig and Ben Reichart gave a log depth circuit for original StringNet model.
Okay.
Generalized one, there is no such work, but probably it still works.
Is this conjecture obvious if it's a classical Hamiltonian?
If it's a classical Hamiltonian, it'll be true because it'll just be like a trivial product state. Yeah, and the trivial product state should be describable by some term of Hamiltonian.
I guess I'm sort of confused. Like this kernel is non-empty. Like, is it obviously non-empty? Because that's sort of like saying.
Oh, I see. So, so these are all projectors, and it is not totally obvious that this is non-empty, but for this class of, so like I will say this. So if you have a general commuting projector Hamiltonian, it will not be obvious if the kernel is non-empty. But for this model, one can show that.
Okay. Yeah. Maybe I should just take this offline.
Yeah. The other question is how to classify quantum phases. Again, the rule is that if two local Hamiltonians, if they are ground states are adiabatically connected to each other, we say that they're in the same phase. In 1D, we have this seminal result, which classifies phases. And in 2D, well, basically, we already know that there are these phases which are non-trivial, such as the toric code. So this problem is much richer. And our work, it doesn't solve these problems in its full generality, but it does in a restrictive setting. All right. So let me just remind you that this is our result. We start from the strict area law state, and then after applying some circuit, we get this ground state of generalized StringNet model. So let me try to explain how this works. Question?
So with respect to like what is known rigorously, do we know that like all of these different computing categories that they are topologically distinct, but we just don't know whether they are all possible phases?
So we know that they are distinct. So if you, I'm not sure if this is written at like a fully like mathematically rigorous level, but there are some papers by like Michael Levin, for example, in which he just shows that two F symbols that cannot be related to each other by gauge transformation, those two states cannot be connected by a constant F circuit. And the hard part is showing that if these abstract data matches, then those two are can be connected by a constant F circuit. This was done for StringNet models by Ludens et al. I think Moore was part of the authors. But in this slightly more general setup, it was not.
Can I ask about that?
Yeah.
So it's a bit weaker than the F symbol actually being related by gauge transformations. Like it's the centers.
Good, right.
Your result kind of captures that.
So our result, so the result itself is just true, but
Can you repeat the question?
right. So the let's see. So the question is right. So here this unit right. So let me try to unpack the question. In this unitary fusion category, there's this thing called F symbol, which you can view as this like a abstract tensor that defines the data. And actually, these F symbols, just because they're different, doesn't mean that they're in a different phase. What really matters is the center of the unitary fusion category. And Don is asking whether our method covers that. And I should have noted that, long story short, yes, yeah. But that heavy lifting was basically done by this work by Ludens et al. So we just use their result. Yeah.
Perhaps just to summarize what
my understanding. This UFC, is that what it's called? Yeah.
UFC, yeah.
Do we know how to classify those ones?
This is beyond my pay grade, but I don't know. Yeah. Okay. So clearly, there's there's some like big distance to travel from left to right, and hopefully, I can give you some idea on how this works. All right. So what are the key approach that we're taking? All the technical tools that we use are essentially just quantum Markov chains. So say you have a tripartite quantum state, rho ABC, and we can define its conditional mutual information as some linear combination of entanglement entropies, as you can see here. And we say that for any such tripartite quantum state, if this conditional mutual information is 0, we say that this is a quantum Markov chain state. And this state is particularly nice because for such state, there's some local recovery map that stitches the density matrix, the global density matrix, starting from local density matrices. So this important result was proved by Petz, who showed that for any quantum Markov chain state, this rho ABC can be written as rho AB applied to some channel, acting on B and sending density matrices B into BC. It should be noted that this condition cannot work for general quantum states, because when this is true, the A and C should have no entanglement, and obviously this is not always true. And quantum Markov chains are very natural objects that appear in these strict area law states, because you can come up with very easy examples of subsystems, like we have here, in red, green, blue. And for these 3 contiguous subsystems, insofar as you accept that the strict area law is true, you can easily verify that this linear combination of entanglement entropies are 0. Yeah, so it goes in all sorts of different ways. Yeah. So it's just, yeah, the real game is like, how do you identify the useful linear subset of subsystems?
Is there a relationship between these Markov chains and what was talked about in the last talk with the commuting?
Good. So good. So there seems to be some passing resemblances. So this structure theorem by Bravi and Vialli, that looks very similar to the structure theorem of structure of states that satisfy this 0 conditional mutual information. So maybe there's something there, but beyond that, I don't know.
So this is the Kawashimoto theorem.
Yeah, that's right. So the heart of this is this Kawashimoto theorem. Okay, so with Bo and Shi and Kutaro Kato and myself, we advocated a more systematic approach to study these class of states, and we call this approach as entanglement bootstrap. So I guess perhaps the most conservative way to think about this program is that you might be a little bit unhappy about this strict area law assumption. One reason is that it's too strong, and our approach does not solve that problem. But the other problem is that there's these numbers that come up, this like alpha and gamma, and you may not be happy that you have to like dangle them around all the time. And this is a formulation which is secretly equivalent to that strict area law assumption, but removes all those junk information that we don't actually care about. So let's consider some physical system on a disk. There are, let's say, millions of qubits. They're so small you can't even see them. And there are, let's say, like 10,000 qubits here, and so that I don't have to draw. And you're zooming up into this region. And locally everywhere, we're demanding some entropic assumptions. So here the convention is that these like solid lines are the actual physical boundary, and the dashed lines are the boundaries of the subsystems that we are going to specify. And the first axiom is basically saying that the subsystem C, which is a small disk-like region, has a 0 correlation with anything that is outside of B and C. This can be verified by just using the purification. Okay. So it's basically a 0 mutual information condition. The other condition essentially states that it's harder to explain, but essentially, this is the main workhorse that allows us to arrive at these quantum Markov chain conditions.
Do you demand this for all sets, or all sets are somehow large enough?
So each of these disks are some constant sizes, let's say radius 2, and we demand for every ball centered at every location.
That's pretty small.
Yes, that's right. Yeah. This is more of a side remark, but even though we only assume this for constant size regions, the same conditions hold at a larger scale as a consequence.
No, I was more thinking the other way around. You sort of say, I only want this to hold for like large enough regions, sort of a weaker condition then.
Oh, I see. So that's totally fine, but outside of those regions, we will not be able to make any statements. Good. And you can also consider systems that are near this boundary, and there you get similar assumptions. So basically, from these assumptions, we want to somehow arrive at this string net wave function. Okay, let me just say like one more thing about the setup. The additional assumptions that we make is that, of course, as I said before, we have this state that satisfies these axioms locally everywhere. But also, on top of that, we can consider some disk-like subsystem in the interior. Okay? And I'm going to assume that for every such disk-like subsystem, which is still finite size, there's a state on this thing, such that it satisfies the same axioms, but now you have this boundary. Okay? And on the boundary, it still satisfies the boundary axiom. But in the interior, this blue region, darker blue region, it matches the original state sigma on that region.
So why isn't sigma, the margin of sigma itself, why do you need some other state to do it for you?
Yeah, so we think, yeah, so this, one part of the proof, to be clear, I think if you assume translational invariance like within this interior, I don't think this is necessary.
It was boundary there.
Yeah. The thing is, we need to do something in this bulk region to actually convert this into a string net, and in doing so, we need to basically create this boundary. Yeah, and of course, when these subsystems are overlapping, we demand that they're locally consistent. This is my assumption. All right. So starting from that, we need to somehow arrive at this. So let me first.
So you don't assume there is a global state.
You don't assume what?
You don't assume that there is a global state.
So we assume that there's a global state here, but we don't assume that there's a global state that with like arbitrary boundary conditions. But that is deduced from the existence of these states. So let me just tell you a little bit more about the final destination that we're going to, which is this string net wave function. And let me just first focus on the actual Hilbert space. Okay, so the Hilbert space of a string net. The easiest way to think about this is that on every edge and on every vertex, you have some finite dimensional qubits. Okay, the standard way in which we describe this is that on every edge, we have we label the edges by some edge labels, let's say A, B, and C. And there's an additional vector, let's call it as like alpha, associated to the Hilbert space here, which depends on this choice of A, B, and C. And I'm just pointing out that this is a standard way in which people talk about this. But maybe a more pedestrian way of thinking about this is that there's a constant dimensional Hilbert space on every edge and vertex. And we just energetically remove anything that. So if we don't want to disallow certain combinations of A, B, and C, we just like add a constraint that prohibits them from being not satisfied. So this is the easiest way to think about it. And unfortunately, this Hamiltonian is 18 local. So there is no way I'm going to explain the actual term in this talk. And the main culprit is this thing. Okay, so you can count that there are 12 edges and there are 6 vertices, so it's 18 local. But what I can explain today is this relatively easier one. It is a vertex constraint acting on each of these vertices. And what it is saying is very simple. It says that, oh, let's say I write down an arbitrary basis state of this string-Nate Hilbert space. I can, without loss of generality, label each basis state in terms of this A, B, C, and alpha. And I'm simply saying that I only allow a choice of A, B, and C if a certain condition is met. For example, if they are from like Z2, maybe I only demand A plus B plus C equals 0, 1, 2. So, and this abstract nonsense, this is all coming from this unitary fusion category, but yeah, if you're really curious, we can talk about that later. All right, and here's the basic overview of the proof. So we start with this ground state that we started with. We start with this sum state that satisfies this strict area law everywhere. And then we're going to apply some local transformations. And this will have an effect of punching the holes, meaning that we will produce these regions that contains this boundary. This will be realized by a depth 1 circuit. And at this point, we will be able to identify some superficial resemblance between this diagram and the diagram that represents the string-Nate Hilbert space. And it turns out that this is not a coincidence, and we'll be able to identify the Hilbert space as well as the vertex constraints. Okay, so let me start with how we punch the holes. So what I drew here is a hexagonal region, which is a zoomed up region of this like a big system. Okay. Again, there are like many qubits here. Again, not drawn. And I will consider a sequence of quantum channels, which applies the following transformation. So we first apply a partial trace in this interior region. And we get this. Okay. It's obviously a channel. And then what we do is that we remember that the strict area law assumption is satisfied. And that allows us to attach these regions by using this PETS map. So what we're trying to do is to attach little pieces of new regions on this part, so that on that region, we produce a boundary. So you get regions like this. And you can repeat this many times until you cover up this interior all by the boundary. And what is maybe a little bit non-trivial is that we never assumed that this state existed in the first place. But the magic of this quantum markup chain is that you can deduce the existence of a new state even though you never started with one. Okay. So note that this entire procedure is completely local to this region. So it is some channel that is acting in the vicinity in this like constant size system. So we can run the same procedure everywhere simultaneously. So that way we can have a depth 1 quantum channel which converts the left-hand side to the right-hand side. And because every local channel can be purified by the Stein spring dilation, we can convert this into a depth 1 circuit with some ancillas. By the way, I should have noted that in this business of classification, it is okay to have additional ancillary systems as well, as long as they're part of states.
Is it also easy to go back
Good. So yeah, indeed it is easy to go back. Basically what you can do is that you can take the partial trace of these boundary regions, and one can show that there exists some channel that basically fills up this interior. This is because of this condition A0, which guarantees that the state can be locally purified. So, all right. So hopefully this first step was not too bad. And at this point, we can draw these two figures side by side and see that at least superficially they look kind of similar. Of course, the proof isn't that easy, but it's a starting point. And from this, indeed, we'll be able to identify the string-Nate Hilbert space and the string-Nate vertex. So to do that, I want to zone in on some particular region, like here. We will call that as a junction. So I just zoomed up that little part. And in particular, I want to focus on this green region, okay? And this region will play an important role. I will call it as M prime. And we're going to do something that looks kind of strange at first. So at this point, we already have a density matrix on this green junction region. And what I'm going to do is to consider a slightly larger set that includes this density matrix as an element, which seems pointless, but there will be a point. And that set will look like this. So I will demand, I will consider the set of states which are locally indistinguishable from the state on this green region. Okay, so I'm still considering a density matrix on the green region. But remember, I started with some density matrix there. I'm looking for all possible density matrices in that region, indistinguishable over these constant size balls. Okay. Good. And then, of course, there's these little regions that have to, there are these little disks that will like go a little bit outside of these green regions. And for those cases, you demand consistency on these larger regions and then trace out back to this green region. And this is what we call as the information convex set. It is just a name. Clearly, this reduced density matrix over this junction is an element of this set by definition. Okay? And what we're going to do is that we will try to rewrite this density matrix that we have originally on the green region in terms of the extreme points of this convex set. So this is a convex set, though, so it has extreme points. And we will be able to decompose that into those extreme points. Obviously, there's nothing controversial. Now, here's the reason why this is actually useful. So for these sets called information convex sets, Rowan and Kotaro and I, we proved this theorem, which says the following. So here's the key part. Sigma of n prime is isomorphic to sigma of m. So it turns out that there's an affine map between the two. And in fact, this is realized by some reversible channel. So this channel turns out to preserve the distance between any two pairs of elements in these sets. In that sense, it is isomorphic. So a non-trivial fact is that for any two regions, let's say m prime and m, which can be smoothly deformed into each other, there is such a reversible channel that maps one set to the other. One way to think about this is to remember that we have these like little PETS maps. You can imagine applying these PETS maps to grow your system, and then you can take the partial trace to like reduce your system. Basically, well, what is going on between these two is that you're applying these sequences of PETS maps and partial traces. I want you, I'll pause for a little second, and this is actually topologically equivalent to that. So maybe pause for 5 seconds. Hopefully you can see that. You can smoothly deform it so that this becomes that. Yeah.
Are all these things deformable to points?
Good. So, but you have to be able to deform it back. So if you deform it to a point, you won't be able to do that.
Oh, okay. Yeah. It has to remain some non-trivial size. That's right. But 2 qubits is fine.
I mean, maybe not 2, but yeah, some constant size is fine. Yeah.
Okay, so I can make this into a little ball if I want to.
Yeah.
Sorry, are the solid lines physical boundaries?
Yes, that's right. Yeah. Yeah, so that's important. Otherwise, if these were like open, then well, who knows what happens out there? Right?
Okay.
Yeah, so you just identified a topological characteristic that it preserves the distance. Like, you know any other type of metric space topology characteristics that are also preserved in your theorem?
Sorry, can you say it?
Do you know like any other type of metric space characteristic that is also preserved?
Oh, I see. Any other metric space characteristics that are preserved? Yeah, I'm not sure. Other than this, yeah. Yeah.
So is the black boundary, are these gap boundaries?
Good. So yeah, this is a very good question. So a very careful audience may notice that here we have a boundary, here we don't. So indeed, this is a gap boundary. And the reason why, the important point is this: the information convex set is a concept that is local to this region. So it is insensitive to what happens at regions that are far away. So you can preserve the information convex set while changing the boundary conditions far away. So actually, there is a non-trivial step from coming here to there. Once you do that, these two are isomorphic. And the reason for doing this is that there is a structure theorem known for the information convex set for these regions. This was done already in 2021. And this again is a non-trivial statement. It says that this set is a direct sum of some objects. And each of these objects are isomorphic to some state space of some finite dimensional Hilbert space. And each of these objects are moreover labeled by some labels ABC, which come from some common label set C. And this corresponds to basically the set of extreme points of these information convex sets of these half-annular region, N1, N2, and N3. You can see that N1 and N2 and N3 can be all smoothly deformed into each other. So the information convex sets are isomorphic. Therefore, there's a natural bijection between the set of extreme points. That's why we can use the single unified label set for all these A, B, and C.
So the ends are the boundaries.
Ends are the boundaries in the, that's right, internal boundaries, yeah, which is still part of this M region.
So instead of saying there's some other boundaries determining what's happening.
That's exactly right, yes, yeah. Actually, it doesn't determine everything fully, because even after you determine that, you still have this state space of some finite dimensional Hilbert space. So there is one extra degree of freedom, even after specifying. That corresponds to the alpha, yes. Yeah. All right. So now we can move this back to the original junction region, and we get something like this. And we have the margin on this junction now can be specified in terms of the extreme points, each of which are specified in terms of these labels, A, B, and C, and the states in the Hilbert space, which is associated with this ABC. Now, let's put this side by side with the original stringnet Hilbert space. So again, okay, so I already told you what that is. And you can see that this is exactly the convention for the stringnet Hilbert space. You have these labels A, B, and C, and in the middle we have this alpha, which depends on this ABC. And moreover, it turns out that for a given choice of A, B, and C, not all choices are allowed. So this puts a non-trivial constraint on individual vertices, and that is exactly the vertex constraint of the stringnet. So this is how the vertex constraint is derived. So this procedure is completely, yeah.
So any level comes from the boundary theory, not the box.
That's right. So this is a very important point. So that's right. The enyon, these labels are boundary enyons, not the boundary.
So in this purification, you need many choices for many different boundary types, and somehow you have to make the same choice everywhere, otherwise you can't join them together.
Good. So yeah, this is a good question. So let me make two comments. So I believe for doing this for one local region, you're okay with this. However, the trouble is that when you try to do this everywhere, we should make sure that we glue all of them in a consistent way, because we'll have some label set here and some choice of the Hilbert space, and somewhere else we may have a different convention. So Yeah. So for the vertex constraints, this doesn't cause a huge problem actually. So it is really at the plaquette constraint that this becomes potentially problematic. At least for the vertex constraint, what we can do is this. So all the junctions, the very general fact about these extreme points of the information convex set is that they can be locally purified. So there is some disentangling unitary on the boundary regions that guarantees to disentangle the interior from the rest, no matter what the purifying system is. This can be guaranteed. So that's why we can apply this disentangling unitary everywhere and get these like little fragments that are completely disentangled to each other. And this at least is okay in terms of writing down the basis states. Yeah. However, when we define these plaquette constraints, it turns out that we have to define them in terms of string operators. And the string operators, a good example is when we have like two different toricodes that are completely disconnected. And remember that sometimes we say this is a E string and the M string in one toricode. And that notion of E and M string might be different in this different toricode. So this example shows that to actually define these plaquette constraints in a consistent way, you have to pick one canonical choice of a single disk that covers all these regions. That's a complicated story, but we managed to find that. Anyway, so this slide is mostly just for the experts. So the plaquette constraint, in the end, you can do this. And the key here is that the result is the result of a fairly long calculation. So the fact that we actually get the string net string net constraint from this like a somewhat lengthy calculation probably suggests that we're doing something right. Okay. So what are the applications? So as I said before, at least for these class substates that obey the strict area law, there's a very simple procedure for proving the ground energy, proving that the ground energy is below something, for example. The reason is that you have this description of the string net Hamiltonian, for which the reduced density matrix is easy to compute. And if the circuit is a constant depth, so you can evaluate the expectation value of any local observables. And the other is this classification problem. It was proven by this very nice paper by Ludens et al. That if you have two string nets, which are Morita equivalent, a very fancy way of saying that they have same anion content, then they can be connected to each other by a constant depth circuit. And because our result converts any state with the strict area law into a string net, we can just use their result to conclude that any two string exact area law states with the same anion content is connected to each other by a constant depth circuit. Okay. So that's a brief summary. Starting with the strict area law state, we arrived at this somewhat complicated model, but still a solvable model. And these are some applications. And future directions. I think probably the most interesting question is, I guess it's hard to judge which is more interesting, but one interesting question is whether the 2D commuting local Hamiltonian is an NP or QCMA. This seems like there's some disagreements, so it would be good to reload that. And either way, I think the answer will be very, very interesting. And I would say the biggest shortcoming of this work is that it is Markov chain condition, which is known to be violated by these spurious contribution to topology entanglement entropes. And it's important to fix that problem. All right, thanks for listening.
Let's take questions offline since we're over time. And we'll be back here again at 3:15 for unrecorded open